The reason that we see anything, especially the reason we see color, is because visible light is reflecting off an object and then shooting straight to our eye. White light, or the typical light you would think is coming from a light bulb or the sun, contains all of these colors. So in order to understand how color works and how we perceive colors around us, we need to look at how that white light reflects or absorbs to create different colors. First off, let's get deep and existential together. What is color? We know red, we know green, we know blue, but what is it? Color is how we perceive light that's either being reflected or absorbed by an object. The colors we see are being reflected off the object to our eye. Every other color that existed in that white light has been absorbed. Objects possess different properties that allow them to reflect specific colors of light and absorb different colors of light. A red shirt is red because it reflects red light and absorbs all other colors. Sunlight or white light has all possible colors of light, which allows us to see all possible colors. We know that white light contains all of the colors because when we refract it, we see all of the colors. The electromagnetic spectrum showed that visible light is broken up by color. The frequency determines the color approximately. Colors to the left, like red, have lower frequency, higher wavelengths. As you move to the right, the frequency increases, but the wavelength decreases. This is that color order, or the rainbow order, Roy-G-Biv: red, orange, yellow, blue, indigo, violet. These colors naturally appear in the order of that frequency. Light typically has three primary colors: red, green, and blue. Combining those colors, we can get different variations. Green and red, light, make yellow. Blue and green, light, make cyan light. Red and blue make magenta light. When we think about primary colors, we need to ignore the instinct to think back when we were kids mixing paint together. When you mixed red and blue paint, you got purple, not magenta. When you mix green and red, you got some disgusting color of paint. But with light, you get yellow. So remember, the primary colors for light are red, green, and blue. This is why when you see some television inputs, their reference is RGB, red, green, blue. That's the signal for the red, the green, and the blue light in older televisions, which were more direct light based, not diode based. When they all mix together in the center, you get white light. This is how we know that white light contains all three, or in fact all shades and all colors in one single beam. We call this additive color mixing because you're moving towards white as you add more colors. If I add green to red light, I get yellow light. If I combine yellow light and blue light, I get white light. Colors that are on opposite sides of this color wheel are called complementary colors. Yellow and blue, because they make white, are complementary. Cyan and red, because they're on opposite sides of white, are complementary. Green and magenta, because they're on opposite sides of white, are complementary lights. For pigment and paint, when we talk about the primary colors, you really need to ignore that voice in your head that reminds you of when you were a kid mixing colors. Because the actual pigment or paint colors, when we talk about primary colors, are more closely related to the printer ink in your printer. If you open up an ink cartridge, don't open up an ink cartridge, your parents will yell at you. You'd see yellow, magenta, and cyan. Yellow is just yellow. Magenta is kind of a pinkish purple, and cyan's a lighter blue. These were the secondary colors for light, just like the secondary colors for pigment is red, or are red, green, and blue, which are the primary colors for light. They're opposite. The primaries create secondary of the other. Paint creates pigment, pigment creates paint. So yellow, magenta, and cyan are our primary pigment colors we mix. When you mix them all together, all three colors, you get black. We call this subtractive color mixing because you're moving towards white as you subtract colors. If I started with all three colors together, I would have black. If I could remove magenta, I'd have just yellow and cyan. I would now have green ink or paint. If I could remove the cyan, I would now have yellow paint. If I removed that, I would have nothing. I'd have white, absolutely nothing. So as I subtract those, I move away from black into light. Complementary colors exist in this color wheel as well. Red and cyan mix together to make black because they're across from each other. Yellow and blue mix together to make black. That's because blue contains magenta and cyan. That's two of the three. Combine that with yellow, now you have all three. In physics, we examine color by looking at the connections between this pigment wheel and the light wheel. So the physics color wheel is based on the three light colors, the three primary colors of light, red, blue, and green. We start with the primary colors of light because we only see color because of light. A blue pair of shoes is blue because it reflects blue. Green grass reflects green light. If I combine red and blue, I get magenta. This is my first primary color of pigment or paint. If I combine blue and green, I get cyan. If I combine my only other combination, red and green, I get yellow. This is really just a re-envisioning of how we look at the light color wheel. You can rewrite it just by the letters of each of the different colors. So we'd start by RB make M, B and G make C, R and G make Y. Drawing this on a test or any other question where you need to analyze color based on light and pigment will be a great reference, so draw it out each time. Let's look at the big ideas that we're taking away from this lesson before trying a couple practice problems using the color wheel. To see a color, it has to reflect. If I see something that is red, it's because it's reflecting red light. If I see something that's cyan, it's because it's reflecting blue and green light. I can only see the colors that are being reflected. All other colors are being absorbed. So if more than one color reflects, I mix those colors. I see the color yellow because yellow is made with red and green. An object that reflects yellow reflects red and green light. If red and green are being reflected, blue is being absorbed. If all of the light is being absorbed, you see black. Black absorbs light. This is why in the winter, if you wear something darker like a black coat, you may stay warmer if it's a sunny day out. That's because all colors that do not reflect are absorbed. When we look at something like a black coat, it's not reflecting red, it's not reflecting green, it's not reflecting blue, it's not reflecting any variation on those colors or any mixture of those colors based on the physics color wheel. All of the light is being absorbed. You can only reflect or absorb the colors that you shine on an object. So if I have a red shirt and I shine red light on it, it will look red. If I shine blue light on it, a red shirt is designed to reflect red. That's why we see red. It absorbs blue and green. Well, we know that if it absorbs all of the color, like all of the blue light, the object looks black. So a red shirt in a blue light would look black. White light contains all colors. So when I shine white light, like the light from a sun or a light bulb, on any object, it's like shining red, green, and blue light. That means it can reflect any combination of those lights or absorb any combination of those lights. Colored light, like theater lights or even the LCD screen on your smartphone, has only the colors that make it up. So if I see red light on stage, that means I have a red light turned on. If I bring any color other than red up there, it's going to look black. However, if I have something that was added together, like yellow light, which is made of red and green, if I wore a red shirt on a yellow light, it would look red because yellow has both red and green. If I wore a green shirt in yellow light, that light would make my shirt look green because yellow light has both red and green. With a red shirt, when it's reflecting red, it would be absorbing the green. With a green shirt, when it's reflecting red or reflecting green, it would be absorbing the red. Regardless, the yellow light can bring out the color that it's given, in this case red or green. Let's try a couple examples. It helps to write out your color chart. RBG down the middle, R and B make M, magenta, B and G make C, cyan, R and G make Y, yellow. Write it out each time or have it on a reference piece of paper. So in this example, why do we see a red shirt in white light? Well, we have to look at the type of light that's hitting it. White light contains red, blue, and green, so it contains those three colors right down the middle. Well, if it's a red shirt, that means it's going to reflect that red light. It can reflect red light because it's given red light. It's given red, blue, and green. So it's reflecting red. If we're seeing red, if it's reflecting red, that means it's absorbing blue and green. That's why we don't see the blue or the green. Whatever colors we don't see are the ones that are being absorbed. Whatever colors we do see are the ones being reflected. So blue and green have been absorbed. What color is a red shirt in a red light? A red shirt reflects red light and absorbs blue and green. So if I put red light on it, it's going to reflect red naturally, based on the properties of what makes a red shirt. Blue and green would be absorbed, but it doesn't matter right now because we're not giving it blue or green light, just red. So red is going to reflect off. If we're only shining red light on the shirt, what colors are being absorbed? Well, we're only giving it one color, and we know it's reflecting that one color. So nothing's being absorbed. Since only red is present, red is shining on the shirt, and that red's being reflected, no color's being absorbed. The shirt would remain red. Let's look at example 2. We have a green bush. Why do we see a green bush outside in white light? There's not a green light in the sky, there's only the sun, which gives us white light. White light has all three colors. It has red, blue, and green. We see the color that's reflecting. So a bush is reflecting green light. That means if it's reflecting green, it has to be absorbing the other colors. It's absorbing red and blue. So whatever doesn't reflect absorbs. This is why we're technically shining all three colors on it, but only seeing one of those colors reflect off. The property of the bush determines what color it reflects, what color it absorbs. The color of the light then allows it to either absorb or reflect. In white light, it's green because it can reflect green, absorb red and blue. However, what color is a green bush in only magenta light? Magenta is made of both red and blue. Well, this bush's properties allow it to absorb red and blue. So if it absorbs all the light we're giving it, it's going to appear black. If it absorbs all of the color that we shine on it, it appears black. We can only see color that is reflected, not color that is absorbed. So red and blue are both absorbed in this case. This is a great example of why we only see the colors that are reflected. Red and blue light are in play here, but they aren't giving us the color that we're looking for. They're giving us the color of the light, which is reflecting off of the white background, but it is all being absorbed by the green bush. Here we have a magenta ornament. Why do we see a magenta ornament in white light? Well, white light has red, blue, and green light. So that means it's reflecting red and blue because red and blue make magenta, which in turn means it's going to be absorbing green light. Whatever isn't reflected is naturally absorbed by the object. If we shine or shone blue light on this, it's going to reflect blue or appear blue. This ornament naturally reflects magenta light. We know that because we can see it as magenta in white light. If it's reflecting magenta light, that means it's reflecting red and blue. It has the ability to reflect red and blue. It has the ability to absorb green. If I was shining red light on it, this ornament would appear red because it can reflect red. So likewise, if I shine blue light on it, since it can reflect blue, it's going to appear blue. There's no color here to be absorbed because only blue is present. This particular ornament reflects red and blue and absorbs green. If I don't give it any green light, it can't absorb any green light. Just like if I don't give it any red light, it can't reflect any red light.